Okay, what we're going to talk about today is implicit differentiation. Okay, and basically what this is used for is when you're looking for the slope, okay, or the derivative, and you cannot isolate one variable. Meaning the function or the equation is all in terms of x's and y's that cannot be isolated. Here's an example. Okay, so here we can't isolate the y. We can't write this as y equals, so we need to derive this implicitly. So most curves are described by formula in the form of y is equal to some function of x, f of x, and we call this an explicit equation. Okay, and this means that you can get y by itself easily. So an explicit equation means you can get y by itself easily. However, it may not always be practical or possible to do that, and when the variables of x and y are all mixed up on either one or both sides of the equation, we have what's called an implicit equation. Okay, so this is when the variables of x and y are all mixed up on one or both sides, and we have an implicit equation. So the way we need to deal with this is derive by what's called implicitly. Okay, and this is just another way of saying use the chain rule. Okay, all right, so the use of the chain rule when you have y, here it says take the derivative with respect to x of x. Okay, so in this case you have x, the derivative of x is equal to 1. Here it says take the derivative with respect to x of y. So you have either y prime, or a lot of times you will see this written as dy dx, meaning the derivative is taken with respect to x of y. Here, because you're taking the derivative with respect to x of x, if you wrote this as 2x dx, because that's what you took the derivative of with respect to, this is equivalent to 1. So this is never written because it would cancel out. So here you're taking the derivative with respect to x of y. So the derivative of y squared is 2y, and y prime, or 2y dy dx. This notation right here is what you're going to see most often, the dy dx. So then you'll be asked to solve for dy dx. And here's an example. So in this first example, we have a curve, okay, that is actually a circle. So in this case, we have a circle. The center is at 0, 0. And our radius is equal to 2 because the diameter is 4. Okay, so we want to solve, or excuse me, find dy dx. So what that means is we're going to take the derivative of this function with respect to x. So we have x squared plus y squared is equal to 4. We take the derivative of x with respect to x, that's when we get that dx dx. This is just going to be 2x plus, if we're taking the derivative of y with respect to x, you get this dy dx notation. So we have 2y dy dx is equal to, and the derivative of this constant is 0. So because we have to solve for dy dx, we're going to move this over here. So we have 2y dy dx is equal to negative 2x, then divide by 2y. So we have dy dx is equal to negative x over y, because the 2's will cancel out. So in this case right here, this is our formula to find the slope, and it's actually in terms of two variables. So that means in order to find the slope, we would actually have to have both x and y. So part of this question is asking us to draw a sketch of the curve, and we'll have to do this with other pieces. So we're going to draw a sketch to the best of our ability of our circle with a radius of 2. And again, it's just a sketch, so it's not going to be perfect. not by any means. But here's our circle, okay, with a radius of 2, and we're actually going to be doing multiple things with this. So here, in part C, it says find d dx of this function. So we have to take the derivative with respect to x, which we actually did in A, and we want to evaluate it at 0. So in this case, because we need to have both x and y, we need to go back up to the original function and solve for our y value when x is 0. So I'm going to do that right here. I'm using the original function, which is all the way up here. So we've got 0 squared plus y squared is equal to 4. Well, we know this goes away, so y squared is equal to 4. Remember, when you take the square root, you get 2 answers. So what that means is when x is 0, because this is a circle, there's 2 solutions for y. We have y is equal to positive 2 and negative 2. So that means we actually have to solve for 2 different slopes. So we're going to find the slope dy dx, okay, when we have the point 0, positive 2, and dy dx when we have 0, negative 2. So what we're going to do is we're going to go to our slope equation, which is right here in green, and we are going to plug in our x and our y values. So what we have is dy dx, plugging in x, we can't have a negative 0, so it's just 0 divided by 2, so this is equal to 0. So at the point 0, 2, which is over here on the graph, 0, 2, I'm going to put this point, I have a 0 slope, which is a horizontal tangent line. So I'm going to sketch this up here. Okay, and this is part C. Okay, so I'll make that in pink. Okay, part C. But we also have another point, which is at 0, negative 2 down here. So what we're going to do is we're going to plug in 0, negative 2 to the slope equation and find out what our slope is at that point. So again, if I plug in my 0 for x and negative 2 for y, it turns out we also have another 0 slope. So these right here are the slopes at these respective points. So I'm going to go over here, and at 0, negative 2, if I have a slope of 0, that means I have another horizontal tangent line. So I'm going to sketch that line. Okay, and this is also part C, so I will highlight this again in pink because that refers to question C. Okay, so then we're asked to find the derivative, or basically the slope, which again we've done in part A, but we want to know what is the slope when x is 1. So we need to go back again to our original equation and plug in 1. So that gives us 1 squared plus y squared is equal to 4. Subtract the 1. Then again, we have 2 values. Y is equal to positive square root of 3 and negative square root of 3. This value right here is approximately 1.7, so it gives me an idea on my graph. So I'm going to go over here, since we had to do this for part C. In part D, I'm just going to plot the points, let's see, dy dx, at 1 positive square root of 3 and 1 negative square root of 3. So now that I know the approximate value, I can go to 1, and then this is about 1.7, so it's going to be on the graph about right here, and I'm making that point nice and big, and then here we have 1 and negative 1.7, so it's going to be down here. Okay, so now we're looking to find the slope. So we're going to go back to our slope equation that we found in part A, and we're going to plug in our values. So what that means is, here, if I'm taking a look, I've got my x value, so I'm going to take the opposite of x by y. Okay, so this is my slope right here. If I were to calculate that, we get negative 1 divided by the square root of 3. It's about negative 0.6. So what that means is, if I were to sketch this, I would have a slope of about negative 0.6. Okay, something like, I don't know, this. Since it's less than 1, I want it to be somewhat flat. And this is going to be part D. And again, I'll use a different color. So let's use orange. And we'll highlight this. And then we have to do the same thing at the point 1 negative square root of 3, which is down here. So then we end up with the opposite of our x value, which is going to be negative 1 over negative square root of 3, which means the slope is a positive 1 over the square root of 3, which we know now is positive 0.6. So we're going to sketch this. So we have a bunch of different lines on this graph. Not a big deal. Here's D again, and I'll highlight that one. And I did all this because here it says illustrate the slopes. Okay. All right, so in example 2, we are asked to find dy dx using implicit differentiation of the cosine of y squared is equal to xy. So instead of moving everything over, basically what we're going to do is we are going to take the derivative of both sides independently. In this case, you may have to use the chain rule, the product rule, sometimes the quotient rule. It just depends on the functions that you're given. So it's in your best interest to make sure that you take a look at each side and derive independently. So in this case, we actually will have to use the chain rule, which means if I take the derivative of the outside first, I end up with the sine, because the derivative of cosine is negative sine. So I'm going to have negative sine y squared. And then you have to take the derivative of the inside. So this is like a plain M&M. Here, this derivative, because it is with respect to, it's the derivative of x with respect to y, we have to use our dy dx notation. So this would be times 2y dy dx. This is all one term, and it's the derivative of the left side. So now I can move to the right side. When I'm taking the derivative of the right side, I have to use the product rule. Okay, so if I said that f is equal to x, f prime would be equal to 1. G is equal to y, so g prime is actually dy dx, because it is the derivative of your y term with respect to x. So what I'm going to do is put that together on the right-hand side. So we've got f prime times g, so this would just be y, plus f g prime, so this is x dy dx. Okay, we've taken the derivative of the entire function. Now we're being asked to find dy dx, and what this means is I actually need to isolate dy dx on one side. So I'm going to actually move this over here, or I could move this over here because this is negative, so I think I'm going to add this to the other side. Let's see. Let's move this here. So we've got basically y is equal to, and I'll do some rearranging, negative 2y, because this negative, this 2y, sine y squared dy dx minus x dy dx. So if we want to isolate dy dx, basically we need to factor out this common term. So we have y is equal to dy dx times negative 2y sine of y squared minus x. I factored out this dy dx. Since we need to solve for dy dx, this is being multiplied, so I'm just going to divide. So we have dy dx is equal to y divided by negative 2y sine of y squared minus x. And you can put this in parentheses on the bottom, or you could leave it open. But this is your final answer. You solved for dy dx. Our last problem is somewhat complicated because both sides are products. So let's call this product 1, and we'll call this product 2. So now when I create my two tables, I can keep them clearly labeled, which is something you should do on your test, quiz, homework. So in number 1, we have our two terms. Okay, so we're going to say that f is equal to x cubed, and g is equal to the cosine of y squared. Okay, we already found the derivative of this over here. Okay, so we should know what it is. The derivative of f is 3x squared. The derivative of g prime we found up in the previous problem. So this would be negative 2y sine of y squared dy dx. Okay, so this is going to be used for this left-hand side. The second one, so I'm doing all this work ahead of time. Here is my table. I've got f is equal to 3x squared, g is equal to y to the fourth, so I took this one, and then I took this one separately. F prime is 6x, g prime would be 4y cubed dy dx. Okay, so I have everything all set up. Now I've got to work with both individual sides. So on the left-hand side, I'm going to use this table here. So we've got f prime times g, so it's these two. So we've got, leave yourself enough room, so you might need to write small, 3x squared cosine of y squared plus, let's see here, f g prime. So this actually becomes a minus. So I need to make sure I have subtraction here. So this becomes a minus. So this will be minus, let's see, we could say negative 2x cubed y sine, so negative 2x cubed y sine of y squared, and then we have our dy dx in there. And again, I just use this table. Is equal to, now I've got this is not as complicated because there's no trig function, so we've got f prime times g, so 6xy to the fourth, 6xy to the fourth, I better make sure, plus here. So these coefficients I can multiply. You've got 12x squared, y cubed, and then don't forget your dy dx. Okay, squeezed in there. So again, since we want to solve for dy dx, that means we need to isolate any term that has dy dx on one side and everything else needs to go to the other. So here I have a term with dy dx and it's negative, so I think I'm going to move this over here and subtract this small term here. So we have 3x squared cosine y squared, subtracting this, minus 6xy to the fourth. Notice none of these have dy dx. Is equal to, this stays positive, 12x squared y cubed dy dx, and then I'm going to add this over here, plus 2x cubed y sine y squared, and then my dy dx is tacked on there too, dy dx. Okay, these two terms right here have a dy dx in common, so I need to factor that out. 3x squared cosine y squared minus 6xy to the fourth is equal to, your dy dx is on the outside, times 12x squared y cubed, that's this part right here, plus 2x cubed y sine y squared, okay, and that's the end of that. So since I'm solving for dy dx, that means I need to move this whole piece right here, this whole thing needs to move over to the other side, so I'm going to divide. So I can say finally that dy dx, meaning I am deriving implicitly, is equal to 3x squared cosine y squared minus 6xy to the fourth divided by 12x squared y cubed plus 2x cubed y sine of the quantity of y squared, and this is your answer right here. So I'll highlight this in green. Dy dx is equal to this whole thing. So really what I would do then is, if I knew my x and my y values, I would just plug in my x and y's and solve for my slope.